Hi guys, and welcome to another HSC chemistry video, this one on production of materials. Focusing specifically today on displacement reactions, how we can remove ions from solution and how we can, work out which ones are most likely to do so. A couple of things that are part of this, video focus is firstly that we have to explain the displacement of metals from solution in terms of the transfer of electrons. So this is redox chemistry that we're looking at here. We need to identify the relationship between the displacement of metals and their reactivity. So we're going to have a quick look at the activity series of metals and try and figure out how we can use that to look at which ions are most likely to be displaced, and we also need to account for some changes in the oxidation state, and we will have a look at that in a little bit of detail later on. So firstly, just as a context setter, two things are happening here. In the first situation, we have a blue solution that is becoming colorless. We have a deposit of some metal sitting in the solution, and that has become coated after some time. So clearly the ion in the first one that was making the solution blue has come out. So we know that solutions are blue primarily due to the presence of copper. So copper is probably the ideal choice here, and so that must be depositing as copper solid. So ions in the solution that are becoming copper solid, and therefore whatever metal we have here is going to be, which looks something like zinc, which is actually going into the solution. So if, for example, this is zinc, then we have zinc ions becoming part of the solution. And zinc ions don't give a solution that characteristic blue color, which is why we've lost the color. In the second one, you can see this is very clearly a piece of copper wire. Now, this solution has gone from colorless to blue. So it suggests that actually copper ions are becoming going into the solution. They're the ones that are doing the displacement this time, or causing the displacement. Now, there's not very many metals that sit below copper on the activity series, and so as a result of that, this must be something like silver, so maybe a silver nitrate. Silver in the solution here being displaced by the copper in order to plate out. So how do we explain all of this? Well, what's happening in a solution is that we have ions, cations and anions. In this case, the anions are going to be spectators. They are not going to take any role in what's happening here. The copper solid, however, is a more reactive metal than the silver. And what it does is it displaces the silver from the solution. So the silver then deposits as silver solid, and the copper goes into the solution and starts to change the color of the solution to see that blue color is starting to appear. So here's the overall equation. Silver nitrate in solution, copper solid, is going to displace the silver ions. It's going to push them out of solution, leaving us with copper nitrate and the silver solid. And this is our deposit. This is our precipitate over here. The general rule is that a more reactive metal will displace a less reactive metal in a solution. So this is really important. The more reactive metal will displace the less reactive metal in the solution. Of course, what that means is if we put solid silver into a solution of copper, so if we put this into a solution of this, then we'll get no reaction. The silver is less reactive, and therefore it will not be able to displace the copper, so we will see no reaction. The more reactive metal will lose the electrons to become a positive ion. So in this case, what we have is the copper, which being a solid has an oxidation state of 0, and what's happened to it is it has lost electrons to become a positive ion. So you can see with the NO3 here that the copper must be a 2+ ion now, and as a consequence of that it would have had to lose 2 electrons. So it's been oxidized. Oxidation is loss of electrons. So here's the little half equation for that, and you can see that we've gone from a 0 to a 2+. The only way we can go to a 2+ is to actually lose the negatives, lose 2 electrons in order for us to do so, and so this is an ox. There's an activity series which gives you a bit of an idea, and you can get a bit of a look at that from the table of standard reduction potentials that we looked at very briefly yesterday. And this will give you an idea of which metals are most likely to displace other metals. So you can see potassium at the top here. If it's a solid placed into any solution, which would be fairly dangerous, it will push all of the others out. So it will even plate out sodium, which is obviously something we don't really want to be doing either. But all the way down. So you can see at the bottom here is gold. So gold is the most stable, and gold will not displace anything from a solution. So basically all you're looking at is anything that sits in behind here will be pushed out. So you can see copper is fairly low, which means if we put iron or zinc or magnesium into a solution containing copper, such as copper sulfate, the copper will always plate out for us. So now we can explain the observation. This deposit is all silver solid that's come out of the solution. The equation is the one up above, and we can look at the fact that the electrons have actually been transferred. So we said that the copper was a 0, the copper ion is a 2+, so that's 2 electrons that have gone, 2 electrons that have gone, and they have to go to somewhere. So what's happened is that the silver was a 1+, and now as it's a solid, it's a 0, so the silver has actually picked up those electrons and effectively has gone from being a cation to now a neutral atom, and it's now plating out in its elemental form. So here's a half equation that represents what's going on here. A 1+ ion becoming a 0. This is a gain of electrons, and the gain of electrons is obviously called reduction. So this is the redox, the reduction component of the redox couple, and as we saw in the previous slide, copper is the oxidation. An activity series is a useful thing for you to have a look at just in terms of which metals are near the top. We said potassium is the most reactive. You'll notice that hydrogen also appears in this table. Towards the bottom it sits above copper, but it sits below quite a large number of these other metals. And the key thing to remember about this is that the more reactive metals are the ones that will displace the less reactive or less active metals in the solution. So this is the important takeaway message from this video. We've also got a little acronym to help us, our oil rig. And we just have to remember that when we're thinking about oxidation is loss, that's the OIL, and reduction is gain, that's the RIG, that it's the electrons that we're talking about being gained or lost. And so when we write these half equations out, we have the electrons coming on the product side for an oxidation and on the reactant side for a reduction. So in 2004, question 19, part A, was a 3-mark question based on this kind of thing. The following experiment was performed to investigate the relative activity of metals. The beaker contained 250 mils of a 0.05 molar copper sulfate solution. After several hours, the dark blue color of the solution became lighter and a red-brown deposit had formed on the piece of zinc metal. We need to account for the changes and provide a balanced oxidation reduction equation in your answer. So what you should notice here is the dark blue color has become lighter, which means that the copper is coming out of the solution. So copper ions are taking in electrons to become copper solid. The red brown deposit, which is formed on the piece of zinc metal, is this copper solid. So that's our copper deposit. And what's happened to the zinc is the one that's actually taken up, solid, is the one that's actually given out those electrons for the copper to take up in the first place. So zinc plus 2 electrons. So this has been oxidized, this has been reduced, and our balanced oxidation reduction equation will be zinc solid plus copper. We can leave the sulfate in if we want, copper sulfate aqueous, to produce copper solid. Switch colors here, and zinc sulfate, which is in the solution. Thanks for watching.